Hi friends, we meet here to start a series of lectures on analog circuits. During this journey into the world of electronics, we shall be discussing diode circuits, transistor circuits, small signal analysis of CE amplifiers, FET, MOSFET and finally operational amplifiers. In today's lecture, we shall be talking about the operation and characteristics of the diodes, the importance of diode in electronic circuits and its ability to conduct current in one direction while blocking current in the other direction, and finally as AC rectifier. The diode. A diode is made from a small piece of semiconductor material, usually silicon, in which half is doped as P region and half is doped as an N region, with a p-n junction and depletion region in between. The P region is called the anode and is connected to a conductive terminal. The N region is called the cathode and is connected to a second conductive terminal. Several common physical configurations of through-hole mounted diodes are illustrated here. These are the typical diode packages shown with terminal identification. The letter K is used for cathode to avoid confusion with certain electrical quantities that are represented by C. Case type numbers are indicated for each diode. Depending on the type of package, the anode and cathode are indicated on a diode in several ways. The cathode is usually marked by a band, a tab or some other feature. On those packages where one lead is connected to the case becomes the cathode. Surface mount diode. Packages shown here are typical diode packages for surface mounting on a printed circuit board. The SOD and SOT packages have gull wing shaped leads. The SMA package has L-shaped leads that bend under the package. The SOD and SMA types have a band on one end to indicate the cathode. The SOT type is a 3-terminal package in which there are either 1 or 2 diodes. In a single diode SOT package, pin 1 is usually the anode and pin 3 is the cathode. In a dual diode SOT package, pin 3 is the common terminal and can be either the anode or the cathode. Always check the data sheet for the particular diode to verify the pin configurations. Diode approximations. The ideal model of a diode is the least accurate approximation and can be represented by a simple switch. When the diode is forward biased, it ideally acts like a closed switch, and when the diode is reverse biased, it ideally acts like an open switch as shown. Although the barrier potential, the forward dynamic resistance and the reverse current are all neglected, this model is adequate for most troubleshooting when you are trying to determine if the diode is working properly. The ideal VI characteristic curve graphically depicts the ideal diode operation. Since the barrier potential and the forward dynamic resistance are neglected, the diode is assumed to have a 0 voltage across it when forward biased, as indicated by the portion of the curve on the positive vertical axis. The forward current is determined by the bias voltage and the limiting resistor using Ohm's law. Since the reverse current is neglected, its value is assumed to be 0 as indicated in figure by the portion of the curve on the negative horizontal axis. The reverse voltage equals the bias voltage. You may want to use the ideal model when you are troubleshooting or trying to figure out the operation of a circuit and are not concerned with more exact values of voltage or current. The practical diode model includes the barrier potential. When the diode is forward biased, it is equivalent to a closed switch in series with a small equivalent voltage source equal to the barrier potential, that is 0.7 volt with the positive side towards the anode as indicated. This equivalent voltage source represents the barrier potential that must be exceeded by the bias voltage before the diode will conduct and is not an active source of voltage. When conducting, a voltage drop of 0.7 volt appears across the diode. When the diode is reverse biased, it is equivalent to an open switch, just as in the ideal model as shown. The barrier potential does not affect reverse bias, so it is not a factor. Since the barrier potential is included and the dynamic resistance is neglected, the diode is assumed to have a voltage across it when forward biased, as indicated by the portion of the curve to the right of the origin. The forward current is determined applying Kirchhoff's voltage law. The practical model is useful when you are troubleshooting in lower voltage circuits. In these cases, the 0.7 volt drop across a diode may be significant and should be taken into account. The practical model is also useful when you are designing basic diode circuits. The complete diode model. The complete model of a diode is the most accurate approximation and includes the barrier potential, the small forward dynamic resistance, and the large internal reverse resistance. The reverse resistance is taken into account because it provides a path for the reverse current, which is included in this diode model. When the diode is forward biased, it acts as a closed switch in series with the equivalent barrier potential voltage and the small forward dynamic resistance as indicated in the figure. But when the diode is reverse biased, it acts as an open switch in parallel with the large internal reverse resistance. The barrier potential does not affect reverse bias, so it is not a factor. Since the barrier potential and the forward dynamic resistance are included, the diode is assumed to have a voltage across it when forward biased. This voltage consists of the barrier potential voltage plus the small voltage drop across the dynamic resistance as indicated by the portion of the curve to the right of the origin. The curve slopes because the voltage drop due to dynamic resistance increases as the current increases. The reverse current is taken into account with the parallel resistance and is indicated by the portion of the curve on the left of the origin. The breakdown portion of the curve is not shown because breakdown is not a normal mode of operation for most diodes. For troubleshooting work, it is unnecessary to use the complete model as it involves complicated calculations. This model is generally suited to design problems using a computer for simulation. Rectifiers. Because of the ability of the diode to conduct current in one direction and block current in the other direction, diodes are used in circuits called rectifiers that convert AC voltage into DC voltage. Rectifiers are found in all DC power supplies that operate from an AC voltage source. A power supply is an essential part of each electronic system, from the simplest to the most complex. All active electronic devices require a source of constant DC that can be supplied by a battery or a DC power supply. The DC power supply converts the standard 220 volt 50 Hz AC voltage available at wall's outlet into a constant DC voltage. The DC power supply is one of the most common circuits you will find, so it is important to understand how it works. The voltage produced is used to power all types of electronic circuits, including consumer electronics, computers, industrial controllers, and most laboratory instrumentation systems and equipment. The DC voltage level required depends on the application, but most applications require relatively low voltages. This basic block diagram explains the components of the complete power supply. It consists of a transformer, a rectifier section, a filter, and a regulator. Generally, the AC input line voltage is stepped down to a lower AC voltage with a transformer. A transformer changes AC voltages based on the turns ratio between the primary and secondary. If the secondary has more turns than the primary, the output voltage across the secondary will be higher and the current will be smaller. If the secondary has fewer turns than the primary, the output voltage across the secondary will be lower and the current will be higher. The rectifier can be either a half wave rectifier or a full wave rectifier. As shown here, the rectifier converts the AC input voltage to a pulsating DC voltage called a half wave rectified voltage. The filter eliminates the fluctuations in the rectified voltage and produces a relatively smooth DC voltage. The regulator is a circuit that maintains a constant DC voltage for variations in the input line voltage or in the load. Regulators vary from a single semiconductor device to a more complex integrated circuits. The load is a circuit or device connected to the output of the power supply and operates from the power supply voltage and current. Half wave rectifier operation. The figure here illustrates the process called half wave rectification. A diode is connected to an AC source and to a load resistor RL, forming a half wave rectifier. Keep in mind that all ground symbols represent the same point electrically. Let's examine what happens during one cycle of the input voltage using the ideal model for the diode. When the sinusoidal input voltage, that is Vin, goes positive, the diode is forward biased and conducts current through the load resistor as shown. The current produces an output voltage across the load RL, which has the same shape as the positive half cycle of the input voltage. When the input voltage goes negative during the second half of its cycle, the diode is reverse biased. In such a situation, there is no current, so the voltage across the load is 0 volt, as shown here. The net result is that only the positive half cycles of the AC input voltage appears across the load. Since the output does not change polarity, it is a pulsating DC voltage with a frequency of 50 Hz as shown in the figure. During the positive alternation of the 50 Hz input voltage, the output voltage looks like the positive half of the input voltage. The current path is through ground back to the source. During the negative alternation of input voltage, the current is 0. So, the output voltage is also 0. Average value of the half wave output voltage. The average value of the half wave rectified output voltage is the value you would measure on a DC voltmeter. Mathematically, it is determined by finding the area under the curve over a full cycle and then dividing by the number of radians in a full cycle as illustrated. The result of this is expressed in this equation where Vp is the peak voltage. This equation shows that V average is approximately 31.8% of V peak for a half wave rectified voltage. Effect of the barrier potential on the half wave rectifier output. In the previous discussion, the diode was considered ideal. When the practical diode model is used with the barrier potential of 0.7 volt taken into account, this is what happens. During the positive half cycle, the input voltage must overcome the barrier potential before the diode becomes forward biased. This results in a half wave output with a peak value that is 0.7 volt less than the peak value of the input. The expression for the peak output voltage is as shown here. It is usually acceptable to use the ideal diode model which neglects the effect of the barrier potential when the peak value of the applied voltage is much greater than the barrier potential, which is at least 10 volts as a rule of thumb. However, we will use the practical model of a diode taking the 0.7 volt barrier potential into account unless stated otherwise. One must also be careful of peak inverse voltage as the diode must be capable of withstanding this repetitive reverse voltage. For the diode as shown, the maximum value of a reverse voltage designated as peak inverse voltage occurs at the peak of each negative alternation of the input voltage when the diode is reverse biased. A diode should be rated at least 20% higher than the peak inverse voltage. Transformer coupling. A transformer is often used to couple the AC input voltage from the source to the rectifier. Transformer coupling provides two advantages. First, it allows the source voltage to be stepped down as needed. Second, the AC source is electrically isolated from the rectifier, thus preventing a shock hazard in the secondary circuit. The amount by which the voltage is stepped down is determined by the turns ratio of the transformer. Unfortunately, the definition of turns ratio for transformers is not consistent between various sources and disciplines. But in this discussion, we use the definition given by IEEE for electronic power transformers, which is the number of turns in the secondary divided by the number of turns in the primary. Thus, a transformer with a turns ratio less than 1 is a step down type and one with a turns ratio greater than 1 is a step up type. To show the turns ratio on a schematic, it is common practice to show the numerical ratio directly above the windings. The secondary voltage of a transformer equals N times the primary voltage, where N is the number of turns as shown in this equation. If N is greater than 1, the secondary voltage is greater than the primary voltage. If N is less than 1, the secondary voltage is less than the primary voltage. If N is equal to 1, then V secondary is equal to V primary. The peak secondary voltage V peak secondary in a transformer coupled half wave rectifier is the same as V primary in as shown in equation. So folks, This brings us to the end of our discussion in today's lecture, and therefore we sum up. The discussion covers the operation and characteristics of the diode, diode models representing different levels of approximation are presented, and testing is discussed. The ability of the diode to conduct current in one direction while blocking current in the other direction is essential to the operation of many types of circuits. One circuit in particular is the AC rectifier, but in this lecture we have talked only about half wave rectifier, and we shall continue our discussion on diodes and other related circuits in the next lectures. So, that is it for today. See you in the next lecture. Thank you very much.